This is the third lesson of Chapter 5, where we're going to be looking at how a living cell would be affected by being placed in different types of solutions. The idea of the ability of a solution to cause a cell to experience a loss or a gain of water from its surroundings is called tonicity. And tonicity is affected by what type of solution that cell is immersed in. There's three different types of solutions based on how much of a solute they have compared to what's inside the cell. If the concentration of the solute in the solution is the same as the cell that's bathing in that solution, then that solution is referred to as being isotonic. And in an isotonic solution, there's going to be no net movement of water in or out of the cell. No particular direction that like the majority of the water is flowing, because it's going to be equal in and out of the cell. And that cell would be said to be in a state of dynamic equilibrium. Let's take a look at that and come back to this slide. I have some visuals coming up here. Oh, there it is. Okay, so the isotonic solution for an animal cell, like a red blood cell, would be slightly salty, like a 0.9% sodium chloride for human red blood cells to maintain their normal functionality. Their shape wouldn't be affected. And as shown in the image at the bottom with the red blood cell, water could go both in and out of the red blood cell, but there's no net direction. It's already in a state of what's called dynamic equilibrium. It's dynamic because it's not static. It can continue to exchange water with its surroundings, but it is in an equilibrium state where the concentrations of the solutes in and outside of the red blood cell are equal. Now take a look at the plant cell. You can also see there's both water going in and out of the cell. So this is also in a state of dynamic equilibrium. But in this state, the plant cell is said to be flaccid. So that word, when referring to a plant, means that it's not maybe standing as upright as it could be. Like, have you ever seen a plant that looks kind of droopy because it needs a drink of water? The leaves might kind of crumble, the stem might start sort of bending, like drooping downward. So that plant might not be dead yet, but once you water it, it will maybe spring back up again and look more firm. So although the plant is not dead, it's really not in its ideal state with this in an isotonic solution. Plants can take on more water. So let's go on and go back to our other types of solutions that can affect a living cell. And then we'll take a look at how that affects both a plant and an animal cell. So the next one is a hypertonic solution. So this is when you have a higher concentration of the solute compared to what's inside the cell. And this is going to cause the cell to lose water, as recall that through osmosis, water is going to go where there's a higher concentration of water to where there's a lower concentration of water. Or you could say that it's going to go from the place where there's a lesser solute concentration to greater solute concentration. So that would be reflected in these examples here of an animal and a plant cell placed in a hypertonic solution. Notice that the red blood cells on the left are losing water and they become very shriveled up. They don't look like red blood cells anymore. They've lost their roundness, and that can be fatal for the red blood cells. This is a phenomenon known as crenation for a red blood cell losing water, and that would apply to all animal cells, by the way, that term crenation. For a plant cell that loses water, it becomes plasmolized. And as shown in the illustration here, When the plant cell loses water, the plasma membrane is pulling away from the cell wall. So that outer layer that still maintains the shape of the plant cell is not necessarily affected by the loss of water, but with the plasma membrane basically being like ripped off of the cell wall, all the organelles are going to shrivel up inside and all sort of be like jumbled together. And ultimately, this is not good for the plant cell. And it could be fatal for the plant that this happens in. This term for this phenomenon in a plant cell is called plasmolysis. So we have crenation in an animal cell, plasmolysis in a plant cell. That should say plasmolysis. Plasmolysis, you could think of it like that. The plasma membrane is lysing or breaking, splitting, ripping off of the cell wall. I can't erase the typo there, but make sure you know there should be an S, plasmolysis. Okay, now, so for either plant and animal cell placed in a hypertonic solution is not going to be a good scenario for that cell. Likely it could be fatal if the exposure is prolonged or the concentration of the solution that's hypertonic is very hypertonic, and this happens quickly. That would also be very fatal to the cell. All right, we've got one more solution type, and that's the hypotonic solution. So it's the opposite of hypertonic. Here you're going to have a solute concentration that's less than that inside the cell, and the cell is going to gain water, again because of the rule of osmosis, that the water is going to move from an area where there's a higher concentration of water to lower concentration of water, or where there's a lower concentration of solute to where there's a higher concentration of solute. So that's this one here. On the left, we see the animal cell taking in water from the hypotonic solution around it. Ultimately, if there's too much water, it can cause the animal cell to burst, like shown here. And that for sure will kill the cell, and it could kill the organism that it's in. However, for a plant cell, it's not fatal. Plant cells can take on extra water and store it in their central vacuole, and this will kind of cause the components of the cell to push outward on the cell wall, creating a situation that is causing the cell to be what's called turgid. Turgid means firm, stiff. It actually is a good situation for the plant cell because this is not going to be those droopy leaves and stems that a plant looks, it's looking thirsty, but it's going to be a normal, healthy plant that can grow upright with its stem. The leaves can fan out fully to optimize photosynthesis and gas exchange. So this is why it's okay to water the plants every day, especially when it's really hot. They can take on some of that extra water and use it to their benefit. But animal cells, no. Ideally, for an animal cell, they need to be in an isotonic solution, but plants can be in hypo or isotonic solutions, but they prefer hypotonic, at least for freshwater plants. Alrighty, so these are all types of passive transport mechanisms that do not require any energy expended by the cell. All of those scenarios that we just looked at. In the next lesson, we're going to consider what happens when a cell needs to use energy to compensate for changes in the solute concentration in the solution that it's in. So stay tuned for the next lesson on that.